Hi, this is a video that goes over 4 of the circular motion problems that we did in class a couple days ago. So the first problem is a 5-meter diameter merry-go-round is turning with a 4-second period. What is the speed of the child on the rim? So I have here drawn a circle which represents the merry-go-round, and it's 5 meters diameter, so all the way across is 5 meters. T, which is how long it takes to make one revolution, is 4 seconds. And there's an equation that looks at the speed at the rim in relationship to the period, which is v is equal to 2 pi r over t. And so we can just solve by putting the radius at 2.5 because the diameter is 5. So the diameter is 5 here, so we're just going to take half of it because we're only concerned about the radius. And then t is 4 seconds, and we get the v value, which is 3.9 meters per second. So if there's a kid here, right here, going around this merry-go-round, she or he would be traveling at 3.9 meters per second. Okay, so the next problem is looking at a roller coaster, and in this case the roller coaster is going in a loop-de-loop here that's 40 meters in diameter. And what it's saying is the apparent weight at the top is equal to the true weight. So the weight of this, which is going to be mg, is equal to actually the true weight, which can be the equivalent normal force. And so they want to know what the speed of the car is. So that's kind of important. When we talk about this apparent weight, we really mean this normal force. Not exactly, but in the problem solving we can say it's the normal force. And the true weight is just the weight of the object. So I'm going to draw a free body diagram here where I have the weight, which is going to be mg, and then the normal force. And I'm saying they're equal, so they're the same thing. In this problem, it's defined this way. The weight is the same as the apparent weight is the same as the true weight. And then I know that the net force is going to be going downward because this is a circular motion and the acceleration is always downward, and it's going to be equal to ma. And I know the AC value is v squared over r. So these are kind of the things I know. I also want to indicate that a plus sign is up and a minus is down. So that's going to help me when I set up the equations. So I'm just going to take this free body diagram and write the sum of the forces is minus W, because this is going down, minus N, which is going down, is equal to MAC squared. So I know that W is equal to mg. Normal is equal to mg because it just says they're equal to each other. And then M, and then v squared over r, which is this equation. So I can cancel out all the m's, and I take 2g is equal to v squared over r. And I really need to put a minus sign in here because the acceleration is going negative. Sorry, I didn't do that. Should be a minus sign here too, and here. So what this works out to is that the velocity is 20 meters per second. That's how fast this thing needs to be going right here in order for this true weight to equal the actual weight. So this next one is the center of gravity of it, and this should say 10 kilograms, that's why this is 10 kilograms, lead ball and a 100-gram lead ball are separated by 10 centimeters. What is the gravitational force? What gravitational force does each exert on the other? So this one is pulling this, and this one is pulling this, and it's the same force. They're equal and opposite forces. The first thing I want to do is I'm going to change these units to sort of the normal units we use, which is kilograms and meters. So those are going to be changed to meters. And then this is the equation for the gravitational pull. The gravitational constant, G, times the mass of the first one, the mass of the second one, divided by the distance between them squared. And the gravitational constant is a constant that's going to always be that. It's 6.68 10 to the minus 11. So I'm just going to put these values in here, do the calculation, and it ends up that the force of gravity on these two to each other is very, very small, and that should be meters per second squared. 6.67 times 10 to the minus 9, oh no, newtons. It's Newton value. It's going to be that many newtons. So the last problem here is a car drives over the top of the hill that has a radius of 50 meters. So this distance here is 50 meters. From the center to here is 50 meters. What is the maximum speed can the car have without flying off the top of the road? So I'm going to draw a free body diagram. I'm going to say there's a weight of the car, and then there's probably a normal force of the car as the road as it is pushing against the car. Also, the the acceleration is going to be downward because this is on circular motion, so the acceleration is traveling downward. Now, what I want to do here is I want to say that there's a point in time where it starts flying off the road. And we want to know just right when that's going to happen. So what happens here is this normal force actually goes to zero when it starts to fly, right? Because there's nothing pushing against it, so it's going to be zero. So if I write the equations this way, minus W plus N is equal to M times AC. And again, here I'm going to say the normal force is going to go to zero, and I'm going to replace W by mg, and then m is associated there, minus v squared over r, because that's the equation for centripetal acceleration. And then I say mg is equal to mv squared over r. I could cancel out the m's, and then g is equal to v squared over r. Putting the values in there, I can get 9.8 times 50 is v squared, and then I can solve for v at 22 meters per second. Okay, that's all the problems. I know I went through that really quickly. Hopefully you can try it yourself, follow it. Okay, see you soon.